Hello, my name is Sophie Baker, and this is a pre-recorded presentation for the 2020 International Conference on Cognitive Modelling. So I would like to talk to you about degenerate optimal boundaries for multiple alternative decision making. So welcome to my poster, that's me in the top left corner. There's a well-accepted normative framework for two-choice perceptual decision making. However, a general normative framework for multiple choices and the characteristics of thresholds therein has yet to converge. So that's the theory that we're interested in developing. So a quick recap: for two-choice tasks, decision trajectories are represented as a particle diffusing in 1D. So applying this to multiple choices, we can deconstruct the SPRT into sequential Bayesian inference per choice. So if you look at figure 1, panel A, you can see the accumulation to threshold per choice. And because this is in posterior probability space, each of these color trajectories at any given point sum to 1. Using the concept of the drift diffusion model, we can use the posterior values as coordinates, and in so doing, that gives us a representation of evidence accumulation as a particle diffusing in ND. So that's panel 2. So here you can see, if you match the colours from left to right, instead of having trajectories evolving in time, we have trajectories evolving in space. Doing this has really interesting geometrical consequences. By representing decision thresholds as diffusing in space, we find that the decision trajectories are constrained to an n-1d simplex. So this example of 3 choices takes place in 3 dimensions but is constrained to a 2D plane. More interestingly, the decision threshold gains a dimension, so is n-2 dimensional. So instead of being single valued with a potential of temporal complexity, instead these can now be spatially complex because they're lines. So the takeaway from this section is that now, by representing multiple alternative decision making as a particle diffusing in ND, the decision threshold shape can be more complex. To explore this, we parameterize the threshold in a general way, given by this equation, and choose 3 exploratory parameterizations. So now we just need to optimize. Because we're exploring the characteristics of these thresholds, we use a stochastic optimization explicitly constructing reward landscapes. So you can see 3 examples of these reward landscapes in figure 3, and then we extract the maxima. So we expected the maxima to be points. Instead, what we found was that the maxima are areas, which means that the maxima comprise of a degenerate set of optimal thresholds. We've investigated this and found that all of these optimized thresholds satisfy the speed-accuracy trade-off curve, and they are qualitatively different too. So where this becomes really interesting is when we tie it in with the current debate over whether or not there is temporal complexity in decision thresholds for 2 choices. So these ideas around urgency signals and collapsing thresholds. So all of the parameterizations that we've looked at are stationary. However, as you move along the thresholds, the average reaction time at each point changes. So there is some link there between complex, nonlinear, static thresholds and threshold dynamics. So to investigate that, we can use a parameter transformation with which we can compare directly with the 2-choice results. And we found that these multidimensional thresholds can mimic threshold dynamics or can appear like threshold dynamics under this transformation. By using sequential Bayesian inference as our coordinates for decision trajectories, we find that evidence normalization, so using posteriors directly as our decision trajectory variables, we can explain some irrational behaviors. Our model also provides an explanation for neural recordings showing an apparent urgency signal. So as we saw in the previous panel, the urgency signals that we're seeing could be results of spatially complex or interdependent decision thresholds. So a quick look back at our conclusions. We found that multiple choice decision thresholds can be spatially complex under a normative framework, which we developed. A degenerate set of high-dimensional complex thresholds are optimal for n alternative tasks. These thresholds produce a range of dynamic structures, and this supports both collapsing thresholds as well as fixed thresholds, and informs part of that debate. And our model, together with its degenerate thresholds, replicates a number of irrational behaviors and satisfies both Hicks law and the SAT sort of offset and slope that we see. Thank you very much for listening.